So we'll primarily look at two strategies for diversity preservation. The first one is called as fitness sharing, where the name is derived from the fact that every individual shares its fitness with all others. So the name is actually extremely bad. So it's just like they are an individual in my population pool. So like nice group of friends, they share their fitness. They let each other know about their fitness value. So every individual has an access to the fitness value of every other individual, which is good. But then now let us see how this thing will actually be implemented and what's the core logic behind it. So the core logic behind this function is, or the core logic behind this diversity preservation is, penalize individuals which are not contributing to diversity. So penalize individuals which are not contributing to diversity, or penalize individuals which are at sparse areas, and incentivize individuals which are dense areas, which are at sparse areas. So if I need to add diversity to this institution, this is exactly what I'll do. If there are some segments of the society which are not represented, I will say the lower marks for them is further reduced down. I would say that those individuals who are not properly represented are given more seats. Those individuals who do not normally qualify but are adding some kind of diversity because they are alone in those areas will get some bonus marks. So I incentivize those individuals, people good in management, people good in sports, I incentivize them up. And if I'm getting 100,000 individuals, okay, that's not our strength. If I get too many individuals which are all more or less providing the same thing, so I'll try to penalize them up. I'll try to deduct their marks. I'll try to say that I have limitations. I cannot take all of you. And that's how I will be encouraging more diverse individuals to actually get encouraged and to work on their diverse means. So now there are two ways by which you could survive. One is you are absolutely great fitness value, amazing fitness value. And the second one is when you are providing something which gets incentives, you are providing some diversity, and the diversity is in terms of a metric called as the sparsity. So diverse individuals are the ones which are alone at one place. There are not many individuals relying over there. Non-diverse individuals are the ones which are grown together at one place. So let's take an example. So after a long time, this is what you expect to happen. So that's what you expect to happen. So these are not providing diversity. So these are dense individuals. Not providing diversity. So I just want to penalize them. I've got too many over here. Finally, I need one individual at good place. There are too many over here, so I penalize them. And these are sparse. So these are adding diversity. So I incentivize. And similarly here, sparse. So I incentivize. Here it may again look opposite. So if you want to find out why diversity preservation in this format is better, I can always draw it in the other way around. So sparse individuals, dense individuals, and again sparse individuals. So I incentivize this. I incentivize this. I penalize these. And I incentivize these. And remember that now I'm actually using geographical distance as a measure. So I am using geographical distance as a measure. Now, in evolutionary technique, whenever you want to incentivize or you want to penalize something, you do it over the fitness value. Just like in real world, if I want to incentivize you or if I want to penalize you, what do? I give you marks or I deduct marks. So plus 5 marks for good behavior, minus 10 marks for plagiarism. That's my metric, that's my economy, that's how I control the scores. So in case of objective function, in case of optimization, it's always a fitness function. So every individual tries to get and do things such that it gets the best fitness value. Every individual tries to do that. And therefore, what I do is in order to incentivize or penalize individuals, I change the fitness function value so that some traits can be encouraged and some traits can be penalized. So I say my new fitness function will be inversely proportional to my and now I make a change, so I write down assume a maximization problem. So if it's a maximization problem, higher fitness is better. Which means sparse individual will have small density and high new fitness function value, and dense individual will have a high density and a smaller fitness function value. So I'm encouraging sparsity, I am penalizing density, and of course my new fitness function value has to be directly proportional to the original fitness function, so that I encourage individuals to go deeper into the minima or higher into the maxima or go more towards the optima. So an individual now will have two forces, will have two intents, will have two evolutionary pressures, one to go into areas which are sparse because of this measure, and the other one to go into areas which are good because of this measure. So my new fitness function value, let us say f dash x is equal to my original fitness value, which is fx, divided by the density of the place. So density of the region at the place where individual x is located. So now what happens is, if an individual is alone, it has small density value, which is good. However, it may have a very bad fitness value. So the overall fitness function is bad because it's alone, but it's at a very bad place. On the other hand, the individual may be alone, but its fitness value may be reasonable. It may not be extremely bad. So this is a moderate value along with a low density or sparsity. So this overall fitness becomes very good. The individual is like, I'm extremely good. So these are those groundbreaking people into arts and sciences. So they are good. They are really good if you talk to them. It's just that they are distinct. So they think cool about themselves, which is correct. It's a moderate fitness value and a sparsity. An individual may be at extremely dense location and it may be good. So again, it's something which is good, but the denominator can become extremely bad. So the evolutionary algorithm just wants to get rid of some individuals. So even though the fitness function is good, this parameter of density is so bad that the fitness function just wants to get rid of them. So again, it discourages some individual. Now here something interesting happens. So let me take a maxima as a problem. So there are too many individuals around over here, but the fitness function is bad. So some individual because of that will get deleted, and as soon as they get deleted, the density reduces, the sparsity increases, which means the individuals are now moderate value upon a moderate value, so it's a reasonably good fitness. So previously we talked about convergence. All individual coming in at one place. Now this has an opposite effect. It inhibits convergence. Which means if it's left to the diversity preservation, the individuals may never converge, but still convergence will happen. Nothing changes in the convergence function, because eventually with time what happens is that the denser areas have an extremely good fitness function value. And because the fitness function value becomes extremely good, so my fitness value is a measure of two things. The fitness function value, it dominates, and because the fitness function value, it dominates, therefore everybody would like to later on go towards the best areas. If something is at bad area, poor areas, the density is small, but the fitness function is also reasonably small. So either that individually slowly comes over the dense areas and improves its fitness, in which case convergence happens, or the individual which is at poor area eventually dies off because of a reasonably poor fitness function value which is not improving. So let's take this as an example. So initially we had too many individuals who were here and very few who were over here. So initially what happens is this is encouraged. So by mutation it improves itself. And this is discouraged. So some individuals go around over here because of diversity preservation. Now, this is not improving, but on the other hand, these individuals will soon start improving themselves up, and hence the fitness of these individuals is better, and as of now, even the sparsity of these individuals is better. So they start attracting too many individuals, which all go around over here. So the diversity preservation plays it to the benefit over here. But now the opposite effect happens. These individuals are too sparse, which is good. These individuals are too dense, which is bad. And therefore they attempt to attract more individuals. However, when you compare the fitness value, these individuals have a very bad fitness value as compared to these. So even if a few individuals go there, these individuals dominate because of a significantly better fitness value. As a result, the sparsity keeps on reducing, and this one keeps on increasing. It's so dense that it has a minimum effect on the sparsity. And because this fitness value is so bad, so the numerator will dominate and it will get all the individuals over here. Even if some individual would have been here, sparse, it would have needed to go here in order to have a comparable fitness value and then get a better fitness because of the sparsity. But then by virtue of mutation, it would have continued to improve itself over here and ultimately going into the population pool. So eventually, all that the diversity preservation does is to delay the convergence like every other measure, but the convergence hopefully happens. And because it's delayed, you know that the chances of getting stuck in local optima are small, and the chances of escaping local optima are large, and the chances of getting in the global optima are better. And of course, it increases the convergence time. Now let's redefine what is density. So I say density is the average distance from all the individuals. So now let me draw it as a fitness landscape into 2D. So that's x1, that's x2, and these are my contours. So I have a x1 over here, and I have got all the individuals over here. So how do I measure the density? I say the density due to this, 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 and so on and so forth. What's the contribution of density of this individual on this? What's the contribution of density on this individual on this, and so on and so forth. So it is a summation of the sharing value of all the individuals I and because it's one of the individuals, let me add I over here and take J over here. So sharing is a function that will be inversely proportional to distance. So if an individual is further apart, it will not contribute anything to the density. If an individual is very close by, it will contribute to the density. So I say share xi xj is inversely proportional to the distance between xi and xj. You can use any function. I will use a specific one. So I use a function that share xi xj is equal to 1 minus d of, so there are two ways I can do inverse, either 1 minus or 1 upon. I take 1 minus. Now I need this or to be always less than 1 so that this term is always positive. So let's divide it by a maximum distance over here, and I want some kind of a curve control by a parameter, so let's take it as alpha, and this equation is only valid if d of xi xj is less than d max, otherwise the term will become negative, which means that after d max it becomes a 0. So that's my share function. And this is my updated fitness function, which has all the philosophy as stated. So what really happens is that far away individuals at whose distance is very large, they don't contribute to the density, which means it becomes fx divided by 1 plus 1 plus 1 plus 1, so on. So it gets reduced, which is correct, that the individual is sparse, and individuals which are very, very, very close by, so d almost becomes 0, so 1 minus this thing almost becomes 0, so it becomes summation of 0 plus 0 plus 0 plus 0 or something very large. So if you are alone, your fitness function is actually very large because the denominator actually becomes extremely, extremely, extremely small. And using a combination of fitness function value and density measure, I could control how the algorithm behaves. Now, there are two parameters over here. The first one is alpha. Alpha is just to control the shape of your density contribution and how sensitive it is to the distance function value. And the second one is the dmax, which is the sharing the radius or the sharing distance. So the sharing distance is up to what radius will the individual share their fitness, or only two individuals which are within the max, which are within the sharing radius, they share the fitness function value. Otherwise, they don't share, they don't contribute. There's also the distance when the density contribution becomes almost zero. So you don't consider that up. It's important from an algorithmic perspective because right now, the algorithm that you can think of is a standard genetic algorithm. So it does selection, crossover, mutation, and then make a new population from the old one. But step number one is fitness function calculation. And if step number one is fitness function calculation, now it's the new fitness function calculation. So the complexity will turn out to be, previously it was n log n. For n individuals, I need to calculate the new fitness function value, and calculation of the new fitness function value is a summation of all individuals, so n. So from n log n, it becomes O(n) square, which is actually pretty large. So what this thing does is only the neighbors matter, and we know that there is a better way to have a proximity query which uses some principles, and when the individuals are sparse enough, it gives you a logarithmic times proximity query. So this is also saying that I'm doing a nearest proximity search within a radii of the max. So it also, in some cases, is responsible for the control of complexity with no change or with no effect on the program logic, that this has to be inverse. So it's 1 minus inverse. And therefore, instead of just taking one equation, I split it up into two parts and said that as long as this part becomes almost zero, after that I physically put it as zero. All the individuals only have non-negative values till the max. After the max, I physically put it at zero. So this is what is the fitness sharing as a diversity measure.